So here's where we left off. I just posted the homework for grades. I'm not sure if they're 100% solid yet. Feel free to come talk to me about it if you have concerns. But as I've been saying all quarter, I really don't think people are coming and talking to me enough. So unless you are Logan, I feel like I should be seeing you more. All right, so at the end of the last class, we were running a context-free grammar for this language that we were interested in figuring out how to parse. So we wanted to say, okay, we want a language that can handle assignments, they can handle prints, and we need some kind of overall structure for the language. We need to put everything under some kind of main function. So the concepts, the non-terminals in this grammar were a program, a sequence, a line, a variable, and an integer, and how we combine those will be able to let us derive the structure or the syntax of an assignment statement or a print statement. So the first one we went through said program arrow main space open parentheses space close parentheses space and then the sequence non-terminal that said these are the terminals, the exact strings that we are looking for to begin a program. A program doesn't begin with main and the open and close parentheses, then it is not syntactically correct. After that main, there's this concept of a sequence. What is that sequence? That is something that we now need to define. Did anyone get a chance to work on this and come up with an answer for the entire grammar? I guess we can talk about it. So here's the full grammar. The colon equals just means defined to be here. So a program is defined to be the terminal main, followed by a space, followed by the terminal open parentheses, space, the terminal close parentheses. These are characters that are typed in the actual program, followed by the non-terminal sequence. The non-terminal sequence is defined to be line or line sequence. I gave you this one as well, and that was to show that we can make a program of arbitrary length. We could write a one-line program after main, or we could write a line followed by saying there's one or more lines to come still, which is what the line sequence represents. A line has two possible now things that it could be. It could either be an assignment statement or it could be a print statement. So a line could either be variable equals integer, since we only care about integers in this language. And the other would be the terminal print space, open parentheses, space, some expression, followed by a space, followed by a close parentheses. So we still need to go define what a variable is, what an integer is, what an expression is. We still need to be able to do that. But at the high level, this is what that breakdown would look like. Questions on this? All right, let's do an example. So we can now start to make a parse tree for the program that we just saw. So we're going to look for this main a equals 4, b equals 8, print a plus b, that program. We now want to draw the parse tree for that. So it would look something like this. we can see exactly what the derivation looks like. So the derivation is just using these arrows to show how the program is derived. So we start with the start non-terminal, that in this grammar is the program. We're going to define that program by main sequence, just like we can in the grammar on the prior slide. We then expand the sequence to be line sequence. And then that line turns into variable equals integer sequence. Then that sequence can become the second line of the program, etc. So you start mapping and unfurling, selecting which expansions you're doing based on the attempt to derive program. That leads us to a parse tree that looks something like this. We can see that for our expression, we basically just used prefix notation. So we can just say that we have a particular assignment syntax that we use. We can say that print now takes that expression will be written in prefix. So we get the plus A, B as the three things we need to define that expression. And an assignment takes a variable and a value. So assign A4, assign B8. And we now have a tree that represents this program. So the question I might have for you is, how do we reconstruct the exact order of the lines in this program based on this parse tree? What algorithm do we use? Depth first search. If we start at the top and always go left until we can't, then we backtrack and go right, we end up going main sequence, blah, 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 blah. We get down to a leaf, and the leaf tells us a statement, assign A4, which if we look back at the program, is the first thing that we need to do. It gives us an instruction for the first actual line of the program. Is it important to parse the main here? Do we need to consider that when we actually go through the parse tree? The answer is no. We wouldn't be able to get to a leaf that allows us to do this in the parse tree because the rules are built into the grammar. So we do not need to go back and verify this start. Because the fact that we were able to construct the parse tree means that it was syntactically valid. But syntax errors aren't the only kinds of errors that we can get, which is why when we try to go analyze this parse tree, that's when we start getting semantics errors. We start getting logic errors. We start getting the kinds of errors that we make more frequently than syntax errors, because IDEs can check that for us. So you can see that we just traverse first line of the program, go back, second line of the program, go back, third line of the program. And this tells us exactly what we need to be doing. Print that, assign this, and the exact opposite order. So it's a pre-order traversal, depth first search. So that's the parsing stage of the compiler. To zoom out just a little bit, we talked about tokenizing, turning a program into a list of tokens, feeding those into the grammar. If those tokens are syntactically correct in a syntactically correct order for that grammar, we can generate the parse tree. With the parse tree, we can now figure out how to run this program. But first, we might want to verify some aspects of this parse tree to make sure that it is semantically correct. So semantics, one of the main parts of semantics is type checking. So that you don't say something like string S equals 4, or int A equals hello. Again, those are syntactically valid. They are an assignment statement. But it does not have meaning associated with what does that mean? What can we do with that? So type checking helps us to allow for and check for semantic errors in the program. Some of the semantic errors force the compilation to halt. We get a compile time problem. When we're looking at the program, we cannot construct the actual statements because the meaning is so broken that we can't do it. Some we can recover from. So a method takes two parameters, an int first and a float second. So imagine now that the method has passed an int and a string. Is this something that we can recover from? Is there a built-in way in any language that you're familiar with for converting a string to a float? Maybe. Depends on the language. But now you can see that that's a decision at the compiler level. When you write such a compiler, you could attempt that conversion for the user. But you have to know what happens if we have a method that is attempted to receive a float. Is it intended behavior? Should I try to do that and then continue the execution of the program? Or is it more likely a bug? And I should stop the compilation of the program and return this to the user and say, is this what you intended? If so, represent it as a float. These become the design decisions behind a lot of compiler decisions. Is this the user's choice, or should I try to do something about that? This is where interpretation can be very useful rather than compilation. Are we familiar with the concepts between compilers and interpreters, how they work differently? We're going to watch something anyway, because I find this to be particularly fun. What is this, 12 years old already? I'm so old. All right, I think we're gonna be able to get sound on this. Let's find out. I love this so much. That is definitely not sound.
Strange convoluted machine language. It's a bit like landing on another planet, whose inhabitants speak an equally strange, convoluted alien language. Getting a mechanic on planet Gobbledygook to repair your spaceship would present the same sort of problem that you have when you want to get a computer to do something. Everything you say has to be translated. And you have a choice between two different sorts of translators. One of them is called an interpreter, and the other is called a compiler. Let's suppose that you've previously written out your list of instructions for the repair of your spaceship. And suppose that you choose the interpreter to do the translating. He reads your first instruction, open lid of rocket engine, translates this into gobbledygook, and immediately passes it on to the mechanic, who executes the instruction. Then the interpreter reads your second instruction, remove spark plug, translates this into gobbledygook, and passes it on to the mechanic, who executes it. And so on and so forth. Now, notice how the interpreter works. He stays with you all the time, and he translates each of your instructions immediately, one by one. This is a rather slow process, because the mechanic has to wait while each instruction is being translated. But on the other hand, it does give you a chance to correct your mistakes as you go along. If the mechanic removes the wrong spark plug, for instance, you'll see this happen right away, and you'll be able to change your instruction accordingly. Compare this with the way the second sort of translator, the compiler, goes about his work. He takes your complete list of instructions, and without further ado, translates the whole lot straight into gobbledygook. He then hands them back to you and goes away, leaving you all on your own. All this has taken some time, but from now on, things will go very fast. You hand the complete list of gobbledygook to the mechanic, and he executes them all in one go. Bang, bang, bang. There's no waiting about this time. But there's one disadvantage to this, of course. If there was a mistake in your instructions, it's too late now. This analogy comes very close to the way the interpreter and compiler translator programs actually work with computers. An interpreter runs slowly, starts right away, and lets you see how things are going. Whereas a compiler takes extra preparation time before your program can run, but then lets it run very quickly, efficiently. To help you remember the difference between an interpreter and a compiler, look at the words themselves. Inter means between. The interpreter is always between your program and the computer, and it translates line by line. To compile, on the other hand, means to pile together. A compiler piles together your entire program and translates the whole thing all at once. Which one you use on Planet Gobbledygook is entirely up to you.
Super short this time, but I find that to be especially relevant when we start talking about how we're going about writing a compiler. So now we see that we need to have defined the rule in advance. If you have an interpreter working with you rather than a compiler, just like you saw in the video, you can see that happen right away. And you can say, oh, that assumed that it was a float, and that's not actually what I want. And you have the ability to right at that point in your program, go make that change. Whereas if you're in a compiler, when you make this decision, there's no stopping point. Someone compiles an entire program all at once, and they don't usually check. They have to run the entire program, and now if the entire output of the program isn't what they expect, they have to go debug it and find the exact point where they went, oh, something thought that this float was actually, or the string was actually a float, when I should have just passed a float in the first place. So it can make debugging a little bit more challenging if the end user makes a mistake. But from a design perspective, you have to figure out what you want to do in general in this situation, rather than make an assumption, and if it's not what the user wants, the user sees it right away. So an int and a float doesn't really usually have a way to convert that. But if you pass an int and an int, now usually there is an int to float natural conversion in most languages. You pass in 3 to a method that's looking for a float, it will do that conversion from 3 to 3.0 and allow you to continue. So if there is a cast that is supported by the language, the compiler can see this, and the compiler can write that cast for you. Which means that you no longer have to think about casting between what could be an equivalent type. Questions on type checking and semantics? At the end of this type checking step, we end up with some intermediate code. We can actually go through and now line by line convert this, just as the compiler was doing in the video. So we end up with some kind of intermediate code. So we are going to go through that parse tree and generate for each line of instruction. We now know that it's syntactically correct and it is semantically correct in terms of types. If we had found either of those issues, we wouldn't have been able to generate the parse tree, and or we wouldn't have been able to generate we wouldn't have been able to match types in a way that makes sense. So now we can actually go through that translation process. So the intermediate code is simpler code, which is nice. Each line will contain references to at most 3 memory addresses. We see this a lot in assembly types of instructions. You don't get very long instructions in assembly. If you were to have a single long instruction, you can break it down into a number of smaller instructions with medium points. So the intermediate code generator is going to go through those lines and convert them into the smaller 3 memory address equivalent form. So if you've taken any assembly courses, have seen assembly instructions, this is usually what that looks like. So let's say we have these 2 lines, sum equals a plus b plus c, sum 2 equals a plus b plus d. Great. The final version of this, we have temp 1 equals a plus b, sum equals temp 1 plus c, temp 2 equals a plus b, sum 2 equals temp 2 plus d. Great. Do we see any ways we can improve this?
Use temp 1 in place of temp 2.
Yes. So the next stage is the code optimizer, because once we have seen this level of intermediate code generation, there are a lot of ways that that can be optimized. You can reuse memory values rather than making, because a read is more expensive than a write, write is more expensive than a read. So you don't want to write a value that already exists into a separate memory address when you can just read from that same memory address. So the code optimizer is going to optimize for efficiency what was just produced. So we've already answered if that code can be optimized. Now we've turned that whole mess into this. It is significantly shorter in terms of the number of instructions that we have to run when we run the program, as well as how much memory that program is going to require to store once it has been the size of that executable in terms of the number of instructions that it runs. Yeah. Questions on that? From here, we can go straight into machine code generation because now we've mapped it very well onto the form of assembly instructions or machine code instructions. So now we can just go translate that optimized code into machine code. So temp 1 equals a plus b has a direct switch into assembly instructions. You just create assembly instructions that the mapping between your programming language syntax and assembly instructions. So you just you write that translation and it's done. You can now take any line that is legal in your language and you have a converter for putting it into assembly. So these are the main steps. Once you have the machine code that is optimized to run on your hardware, then you can run that program. We have the translation process complete. The compiler will optimize this process by storing some extra information. That information will allow you to compile faster. So there is a symbol table. A symbol table just stores things like your variable names. If you say my program contains a variable called sum, great. We're going to have a table now with the term sum and the value of sum. If sum is an integer, then there will be some integer value associated with sum. Function names, if you try to write a function and says, all right, I'm going to make a function called food, then we'll store the name of that such that eventually when you call foo, it's a lookup to a symbol table that says, is there a value for this term that is not a keyword in the language? So when you define this, when you write a function, you either need a separate program to first analyze and find those, populate the symbol table, and then run it. Or if you're looking for efficiency in a language like C++, then you have a header file that defines that all of these are going to exist. So we would first parse the header file to fill the symbol table that says, what I'm looking for are, here are all of the function names, and here are all of the parameters that we expect associated with those functions. And that way, when I go read the code and I see a function that is declared, I can say, does this map to a function that I was expecting to be here? Because in Java, for instance, you can write functions in any order. One of the reasons Java is slower than C++ is that we have to actually go verify. We might see some method declaration before it is called. Or we might try to call a function and not know whether that function is legal or valid yet or not. So you need two passes over the long program. One to populate the symbol table, and then one to make sure and verify that you are following the associated syntax that you've outlined in terms of, are you calling them correctly with the associated number of parameters? Are those parameters map to the associated types that are expected? Again, if you have a header file, a much shorter file, that allows you to write the associated source file in whatever order you want. If you don't have a header file in a class like C++, then you need to define the function before you call it. So you get extra steps involved with, from the programmer's perspective, needing to keep in mind what order things are in, because if you try to use something before you've defined it, the compiler isn't going to go search for it for you because it's designed for efficiency. So as we scan, we recognize identifiers, we add them to the symbol table unless they're already there. Parsing adds the information to the table, such as the variable type as you go find it. And then type checking will refer to the table to make sure that it's all flowing. You can also do some error checking at the compiler stage. So when we scan, we may have a word that doesn't match a particular token type. In parsing, we may have some ordering of words that don't match some legal syntactical construct that we have defined in the grammar. If we find an error, we need to figure out what kind of error it was. The line number that it was on, whatever information we can gather from this, we can return as an error to the user to help them to debug. And you will note that anytime you've ever failed a compilation step or tried to run something and you end up with an error, you always get a line number associated with it. You always get some information back from the computer. And that's usually part of these programs that are meant to figure out what kind of error happened and where it happened. Any last minute questions on this before we dive into the actual guts of the parsing step? We actually don't have time to go over every single one of these in more detail than this. So I have highlighted the parsing step as one that is most related to what we've covered so far in the class, and we're going to take a deeper dive into how to parse a program, because it will involve things like analyzing grammars that we have looked at. So that is where we are going next, unless anyone has any questions. All right, so. We know what parsing is at this point. We've seen it happen. We know at a very basic level what it is, but. What did we look at? We talked about the parsing problem a little bit earlier. What algorithm did we talk about that is, at least at some stage, parsing? CYK, yeah. So let's refresh us on CYK so far. What was CYK? How efficient was it? Why did it work? Or what's it trying to answer?
It wanted to see if a production or like if a given string could be made from a production.
Yeah, we have a grammar and we want to say, is this string a member of the language defined by this grammar? So it answered the membership problem. Do we remember what the efficiency of CYK was? It was cubic. Yeah. It was a dynamic programming algorithm that took something that in brute force required exponential time and gave us a polynomial time, a cubic time solution for it. It was nice because you could determine that membership problem. You could answer yes or no. It wouldn't ever enter an infinite loop if it couldn't be produced. We would actually be able to determine, no, this cannot be produced. So exhaustive search parsing, we start with the start non-terminal. And we match every possible non-terminal rule to see if we can generate the program. The issue that we're going to run into when we do an entire program is cubic is too slow. So we're going to try to find something that at least sometimes allows us to be faster. Is there some pre-work that we can do that allows us to match this even faster? The other issue we can run into is that we have multiple productions for a particular left-hand side non-terminal. So A arrow something, A arrow something else. Now we need non-determinism because we either need to find a searching algorithm to deterministically go down that path, or we need to somehow be able to provide infinite parallelism, which of course we can't do on our deterministic machines. So we solved this with CYK. It had to be in Chomsky normal form, but that was exhaustive search parsing. LL parsing, on the other hand, is going to be, we looked at it very, very briefly earlier in the quarter, but here's where we're going to bring it back and explore it in more detail. So we looked at it briefly, it's time to look at it in more detail. So there are a couple of different general parsing approaches. The first is kind of what CYK does. We're top down, we start with the start non-terminal, and we're eventually going to determine, can we derive this entire string looking from left to right, replacing non-terminals with productions that are equivalent to that non-terminal. So both exhaustive that we've seen and LL parsing are top down. Because we start with that start non-terminal, it's exactly what we started with CYK. Bottom up, on the other hand, is going to start with the symbols in the string and try to replace them with non-terminals with an attempt to derive the start symbol. Does that make sense how one is top down, the other is bottom up? Start with the start non-terminal, can we produce the string? Start with the string, can we contract it? Try to get that start non-terminal out of it. As we have time next week, we're going to start looking at LR parsing as a bottom-up approach. So there are efficient ways to do both of these. And it turns out that they have different uses, so it's actually worth studying both of them. So let's give you an example top-down parse. Here's a grammar. Go ahead and construct a leftmost derivation and parse tree. that parse tree look like? Remember, if we're constructing a parse tree, we're gonna have a root node that represents the start non-terminal. And then we have child nodes that can either be terminals or non-terminals. Children, I guess, leaf nodes are always terminals, and if they're non-terminals, then they're internal nodes that need to be expanded. The fun part comes when you have an OR. So we either need a string to match it to say, how would this grammar generate that string? Or we need some optionality built into it, some separate parse trees that represent the different options. So you end up with something that can look like this. I think it's needed a string associated with it. I'm struggling to see what the point of this was. So this would generate the string AABBCBC as a way of saying, okay, great, now we can start at the start non-terminal, we can apply these rules successively to generate a particular string that we care about. And we can now see that applying these rules, the string AABBCBC is in the language. But we started with the start non-terminal for this. So this tree really represents a top-down approach. A bottom-up approach would allow you to, if this was how we were generating AABBCBC, you could start by looking left to right across these sets of characters, and you will see that AAB, okay, we can take this B and we can convert that into the non-terminal A. And now we have AA capital A, which can also be derived from A. From there, we continue reading the string, and we see that the C that we get to can be represented by a B. And then B, capital B, B can be condensed into a capital B. And now we have lowercase a, capital A, capital B, lowercase c, which was that rule in the grammar that we needed. A, capital B, C, that derives the start non-terminal. So we started by taking a look at the string's nature and trying to reverse the top-down process and find ways that we could condense them and eventually derive the start non-terminal. So it's really just the order in which you're doing things. You always have that level of optionality, regardless of the direction that you're going. To be able to understand the top-down LL parse, we need to define a couple of reasonably complicated ideas. The first is what we're going to call the first function. The issue that we run into if we're trying to effectively answer the membership question is, which production rule should we apply when there are multiple production rules for a particular non-terminal? So if we are in that case, then we need some functions that we're going to use both in LL and LR parsing. We're first going to use it in LL parsing. So the first function says, given a context-free grammar, first is going to tell us the first terminal that can follow, sorry, the first terminal that can be produced in any string from that non-terminal. So first of S says, what are all the first terminals that could start a legal string in this language? First of A would say, given that we have the non-terminal A, what are all of the first terminals that could appear in some sequence of productions replacing A? First of a terminal is just the set that includes itself, nothing else. From this, it basically tells us from left to right, what is the, it's just better to get into an example. I guess these rules are pretty important. So first of any particular non-terminal starts with just the empty set. And as we explore the grammar and continue this process, we can union that with the first of elements of it to be able to get the first of that non-terminal. The first of an entire production is the first of the first symbol in the right-hand side of that production. So here's an algorithm for it. Let's give you an example because I feel like that didn't really do it justice in terms of what it actually is. And as always, examples are way more important. We'll come back to this after this first example so that it makes more sense. So first of S for the following grammar. So first of S can produce one of two different productions. We want to know what are all of the characters that a string defined by this grammar could produce. So if we look at the left-hand side of this, what is the first terminal for any production that's derived by the left-hand side of this production, or the left-hand side of these options? It always has to be A, right? So the idea is we're going to start by saying first of S is the empty set. But we're going to start to union this as we explore the grammar and find more and more characters that could start an associated string. So we're going to union this with first of lowercase a, which in the rules on the prior slide we said is just itself. So first of a terminal is itself. Union, we now need first of this non-terminal. This is a separate problem we're going to have to go solve in order to be able to solve this entire problem. So now we need to define first of A. So when we look at what A can become, what can it become here on the left-hand side? Just a B. So we're going to say this is first of the terminal B, which is just B, union first of the terminal C, which is just C. So now we get here is the set BC. So that becomes the answer to first of A. It is the set BC. And now we union all of these together. So this is really the set that contains A. So the empty set union A, union B and C says that we can replace all of this with A, B, and C. And this is the process, the algorithm for determining what can start a string in the language. So now, if we are asked, does the string DDD is that in the language defined by this grammar? You could immediately go to the first character and say, is that in the set of first of S? D is not in the set first of S, therefore that string is not in this grammar. And you answer it with a single query. You do this work ahead of time, and you can start answering questions about the membership question way faster than you can even with CYK. So now, with that example under our belt, I think we can go back and talk about exactly the work on the past slide. Did all that make sense? Any questions about that algorithm? So first of a terminal is the set of itself. First of a non-terminal starts as the empty set, and we add to it, we union to it as we explore the grammar. The first of a left-hand side is the first of each production in the right-hand side. The first of a production is just the first symbol in the right-hand side of that production, which is the set of rules that we just looked at. So here's the algorithm. This is what I just went through in solving that. You can refer to this at any point to help you. So, cool. We were able to answer this. It turns out, though, that there are some grammars that are a little bit more challenging than this. How would we work this one out? We have about 1 minute left, so we're gonna think about this and we're gonna come back to it tomorrow and get an answer. But how would you calculate first of S for this grammar?
If there's nothing on the left side of a non-terminal, would it mean that there's just nothing there? Like, for example, we don't have any character in that set from the essay production, so we just use the B.
Logically, that would be yes. If we follow what I just went through, though, we would be doing an infinite recursion. We would be defining first of S in terms of first of S, which we need to evaluate. So we evaluate first of S, and part of that needs to be that we evaluate first of S. So intuitively, you're absolutely right, that there's no way that this A can ever start the string. Right? It's always going to be B. How would you get that out of its rules? How would we do that according to what we just talked about? So first of S is first of S union first of SA, union first of B. First of B is just B.
Just treat it as like an empty string.
Yeah, if you end up doing it with itself, first of S defined in terms of first of S, we can kind of start to ignore that, because there's no way for this to be anything other than everything else that it's defined as. So we just get, it is first of S, union first of S, union B. We ignore the first of S there, because there's no way for it to be anything other than that. So we just get the set B. I'll leave you with one nugget of where we are headed. And that is when we have lambdas in our grammars, this definition gets just a little bit harder. So sleep on that, and we'll come back tomorrow and figure that out. I will be revealing an assignment today that is going to be the last assignment that will be due next week. Not next week. Yes, next week. Next week is last week's class. That has to be the case. So look for that. It will be the longest homework of the quarter with significantly more points than most. So significant amounts of recovery possible. See you tomorrow.